Good morning, everyone. My name is Yuhua Chen from Cedars-Sinai Medical Center. Today, I'm very happy to introduce our new method named ultrafast coronary MRA by generative adversarial superposition to dramatically accelerate scan time. I have nothing to disclose. As cardiovascular disease is the primary cause of mortality in the United States, cardiac MRI is unique in its flexibility for assessing multiple aspects of the disease, including anatomic, perfusion, function, and tissue characterization, which are powerful tools for evaluating various myocardial pathologies. However, coronary MRA has lagged behind in cardiology due to limited resolution and significant time requirement. For CTA, it takes about 3 seconds to image. MRA takes more than 7 minutes. What if we can make coronary MRA much faster, for say, in a breath hold period of 15 minutes? That will allow us to be included into clinical CMR protocols. In light of recent studies such as the informed trial demonstrating the potential roles of CMR in assessment of coronary, we believe that the absence of coronary assessment in CMR is a major limitation of cardiac MRI. We propose using a superposition technique to make a basic coronary assessment accessible in all patients receiving CMI by the addition of a 15-second single breath hold sequence augmented by artificial intelligence. But how can we achieve this high acceleration ratio? We can gain speed at the cost of resolution. As shown on screen, the most time-consuming of the imaging is to capture the data lines in the phase encoding directions. If we only capture 1/16 data at the center, we can accelerate 16 times faster. But of course, images are very blurry. But how can we improve the resolution of the fast MRA? One technique is called single image super resolution, which makes use of the state-of-the-art AI models to convert low-resolution images into high-resolution by chaining them with low-resolution, high-resolution image pairs. By adding generative adversarial networks, aka GAN, we can further improve the image quality of a SR image, which has visually indistinguishable fine details, as we can see on the screen. Therefore, by learning the transformation from low resolution to high resolution images, we should be able to revert the blurring effects of downsampling and recover the anatomical details. This enables MRA with faster scan, higher SNI, and very easy to implement because it is post-processing based. However, training data for coronary MRA are very limited. We propose to incorporate brain MRA datasets, which are more available in a large data quantity and share more important image features like visual structure. Here are the composition of our cross-domain data used in this study. We have about 100 contrast-enhanced coronary MRA, wherein patients will be performed an ICA later. On the brain dataset side, we have about 500 subjects. Data is further split into chaining, validation, testing, as shown here. All evaluation was done on the coronary MRA dataset. To address the challenge of higher acceleration ratio and cross-domain training data, we introduced our deep learning model DRAGAN-Domain-Robust Adversarial-learning GAN. It is based on the most popular NDCR SRN structure with some modification on the discriminator subnetworks. In DRAGAN, we add a feature classifier to increase model's robustness over different types of data like coronary versus brain image. On top of our innovation architectures, we also improved SR results by introducing two-stage training approach. Conventionally, the low resolution is fed into the network and the SR images out directly. However, we found that if we can split the process into train a non-GAN network first, and then recover the main structure, and then we get the fine details by another GAN network, we can further improve the fine details with GAN. This two-stage training doubles model capacity without breaking the computer memory. In this experiment, we first reduce the resolution of MRA by case-based truncation. Then we train the model to recover the sharply to get super resolution images. Then we compare the original resolution, super resolution, and other upsampling results to evaluate the performance. Here is the image quality measurement in numbers. The first part shows the results for a non-GAN network, which mainly to recover big structures. By training on both datasets, the John chain model obtained the best number in the similarity matches such as PSNI and SSIM. The second part shows the comparison between different GAN networks. We can see the DRAGAN outperformed all the others, especially in the perceptual scores, where a lower number is. Here is one random selected sample to demonstrate image quality comparison between different upsampling methods. When zooming, we can see that training again only on 40 coronary MRA results in distortion on the edges. More dangerously, adding phase structures, but with DRAGAN, the artifacts are just gone, and its output is closer to the original resolution images with the same level of sharpness, which are good. We further evaluate our DRAGAN for diagnosing stenosis. All MRAs from original resolution, DRAGAN outputs, and interpreted images were de-identified and mixed. A cardiologist who was blinded to the image type to a grade A segment for larger than 50% stenosis in the scale of 1 to 4, as well as reading confidence from 1 to 4 as well. Let's look at the confusion matrix of the stenosis readings. On the left, it is the high resolution reading in the horizontal direction. On the bottom, it's the low resolution and super resolution reading in the vertical directions. We can see in the super resolution provides more correctly negative stenosis readings, as we can see here, higher number. And it has also much less false positive, as we can see here. For the positive stenosis reading, super resolution reading is also more correct. We can also see a similarity in the confidence. Segments are clearly dissipated in high resolution, became very challenging in low resolution, while super resolution is much more consistent with high resolution MRAs. Here is statistic of the reading accuracy. DRAGAN achieved an AUC in 0.84, having an overall accuracy more than 80% compared with high resolution MRA reading as well. For the first representative case, we can see there is 80% stenosis in the mid-LAD from QCA reading. The original high-res MRA has a correct reading with very high confidence, while the low-res MRA can barely see the segment. DRAGAN provides same correct results and also have a clearly vision on that. For another patient, we can see there's a 95 stenosis in proximal LCX from QCA reading. The original high-res MRA has a correct reading with very high confidence, but interpreted image is unable to provide useful information. Our DRAGAN provides same correct results with a high confidence. So overall, we demonstrate the feasibility of using a deep learning network to substantially improve the image quality of 16 types undersampled coronary MRA. Blind readings show that promising accuracy in detecting lumen stenosis. GAN-based network and John training with brain MRA were both beneficial and generate the best results. And we are working on prospective undersampling and systematic validation with array and geographies. Thank you very much for both the team from Cedar-Sinai and Shenwu Hospital.